SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Advanced Thermodynamics and Combustion, Module 8, Combustion and Flames. So in this module there were 5 lectures, out of which we have covered laminar premix flame, laminar diffusion flame. Today we are going to discuss about another concept, what we call as droplet evaporation and droplet burning. In this lecture, that is lecture number 31, droplet evaporation and droplet burning, we will touch upon the following segments: the concept of droplet evaporation through mass transfer, droplet evaporation through heat transfer, and finally the droplet burning. So essentially, when you look the application of this concept of droplet evaporation and burning, you may be aware that in a diesel engine combustions we inject the fuel through an fuel injectors, and the fuel, when it goes to the engine cylinder, this engine cylinder is already at elevated pressure and temperature that has happened during the compression stroke. Now at this elevated pressure and temperatures, fuel is injected. Now when the fuel comes out of the fuel injector, it comes as a very tiny droplets, or that droplets, the safest way to assume those droplets to be in the spherical shape, and there are many or infinite number of such droplets which goes into the engine cylinders. Now after this droplet, what we can see is that in the engine cylinder itself there are a difference due to temperatures, because already the compression temperature is already at elevated pressure and temperatures, so temperature is also too high. Other aspect is that there can be possibly the effect of concentration, that means in that cylinder there may be some pre-mixed concentration of the fuel, that is one aspect. So when this droplet comes, it sees two effects. One is the concentration difference that remains within the droplet and it's outside the droplet. Second effect is that the temperature difference, that means within the droplet and ambient temperatures there is also a difference. So there, when the droplet evaporates in the engine cylinder, there can be a mass transfer effect, there can be heat transfer effects. This mass transfer effect is associated with this concentration gradient, and this heat transfer difference is associated with temperature difference. And side by side, when the fuel ignites, so because in diesel engine there is a self ignition, the fuel ignites and there is a formation of flame, localized flame at multiple locations. So in that sense, when there is a formation of flame, the two effects become predominant and this droplet starts burning. Now when this droplet starts burning means like the fuel already goes into combustion mode. So when this droplet burning means initially fuel has come with small tiny bubbles, and finally those bubbles disappear, combustion has completed, and that we call it as a droplet burning. And this concept of droplet burning comes into pictures when the flame is already generated within the engine cylinders. So to get the combined effect of both mass heat transfer, that means in a droplet burning it leads to have a combined mass and heat transfers. So in our lecture today we will touch upon some concept of mass transfer while droplets formation and evaporations, concept of heat transfer for droplet evaporations, and we will combine both of them how it gives a physical picture in the combustion mode. So, this is the essence or moral story of this lecture. So, to start with, I will talk about first on droplet evaporation by mass transfers. As you can see here that when the fuel droplets can be considered as a spherically bubble, and the droplet starts and its radius keeps on changing. Its radius is a variable number. I mean, the size of the droplet depends on the size of the radius, and within this spherical bubble there is some concentration of the fuel, and outside this sphere this what we call as far field or ambient, and this concentration is something different, that is in this case I have mentioned is Ya infinity. So, there is a concentration difference within the sphere and the far field, and if you look at the boundary or interface where we actually start x is equal to 0, there we can say that within the droplet it is in the liquid phase, and within the gas outside the sphere it is in the vapor phase. So, for the droplet to evaporate there must be some exchange of heat, and due to this exchange of heat the fuel droplet diffuses into ambience. So, this is the concept of the droplet diffusion into ambience. To summarize this droplet evaporation concept by mass transfer, I have highlighted some of the important points. And the non-premixed combustion system involves evaporation and burning of spherical liquid droplets, and for which we all need to require or you need to frame the governing equations that will allow to explore the size of the droplet, ambient condition of the droplet evaporation and burning time. And in fact, this knowledge is required because it is very important for the design and operation of practical devices. To start with, what we look at is the evaporation of a single liquid droplet in a quiescent environment, and when we do that, a best way to represent them is the spherical coordinate systems. So, physically the heat from the ambient environment supplies energy necessary to vaporize the liquid, and the vapor diffuses from the droplet surface to the ambient gas, and the mass loss causes the droplet radius to shrink. That means, when it evaporates the droplet radius shrinks to a 0 size, and there we say that droplet is completely evaporated. And to do this analysis or to do this mathematical modeling, we need to involve the conservation laws for droplet, where you need to recall the mass and energy conservations. We also need to recall the droplet vapor and ambient gas mixtures, where we require overall mass conservations, droplet species conservation and energy conservations. And for this, to analyze this, we have to frame certain assumptions for our mathematical understanding. The first one is evaporation process is quasi-steady. This means that process can be described as if it were in steady state. The droplet temperature is uniform with some fixed value below the boiling point of the liquid. The mass fraction of the vapor at the droplet surface is determined by the liquid vapor equilibrium at the droplet temperatures, and all the thermophysical properties for the droplets are treated as constant. So, when we look at this droplet evaporation through mass transfers, what we see is that your initial concentration which was inside the droplet was Yas, which is typically the maximum at the surface. Rs is nothing but the radius when it has gone to the maximum size at the surface. So, it is the surface, the concentration happens to be initially at this value Yas, but however ideally it should have been 1, and when the radius keeps on increasing, when you are going with along the radius, this concentration drops. That means, there is a diffusion of the droplet species into the medium, and this medium was initially concentration was Ya into F. So, here one point that I need to emphasize is the fact that we have the same species which was initially in the liquid phase and it goes to vapor phase, and that species only diffuses into the medium. So, there is no third species, only fuel, oxidizer and product, these are the three species, but it is only the concentration difference that happens is mainly for the fuel. I am not going to go the details into derivations. We need to recall the mass conservations. We also need to recall species conservations by invoking the Fick's law, and important condition is the boundary conditions. Boundary conditions what we look at when r goes to infinity, that means at very high value your Ya goes to Ya infinity, there somewhere you have Ya infinity this value, and when r goes to Rs, so Yas is the concentration at the surface. So, based on this we can now find out the evaporation rate for the droplet by an expressions which is the m dot, and it is equal to 4 pi Rs into rho dAB ln 1 plus By. So, Rs you know that it is a variable radius or radius liquid vapor interface radius, rho is the nothing but your density, dAB is the binary diffusion coefficients, and here we introduce one parameter what we call as By, which is called in the combustion terminology we call this as a transfer number. Basically it is nothing but the ratio of the concentration difference at the surface and far stream divided by Yas minus Yas infinity divided by 1 minus Yas. So, this is the transfer number, and its main significance is that that transfer number is defined with respect to mass transfer, or we can say mass fraction of the droplet vapor. So, main significance is that when the transfer number is 0, evaporation rate is 0, that means there is no droplet that gets transferred. So, that is no evaporation rate. With increase in the transfer number, the evaporation rate increases. So, this we can catch hold of from this evaporation rate expressions, m dot is equal to 4 pi s rho into dAB into 1 plus ln By. So, here you remember the word transfer number with respect to mass transfers. Now, once you have this transfer number, you now can see that when the droplet comes out of from the injector, it has some finite diameter or size, and finally the diameter vanishes with time. That means when the fuel droplet evaporates, that means that the droplet vanishes. That point of time the diameter shrinks to 0 or Rs tends to 0. So, when that condition happens, we call this as a droplet lifetime. So, droplet lifetime means the droplet size which was initial diameter d0, it shrinks to 0 diameter at certain time frame, and that time we call this as a droplet lifetime. And so, droplet lifetime with respect to this mass transfer diffusion can be found out by considering the droplet mass conservations, which says that the rate at which mass of the droplet decreases is equal to rate at which the fluid is vaporized. So, dmd, that is mass of the droplet, by dt is minus m dot. So, we know that it is a spherical volume, we know its volume, and we also know that its density, and typically when you say the density, we recall that the density of the droplet in its liquid phase. So, by putting this we can define a parameter what we call as evaporation constant, and that evaporation constant is a function of this transfer number. So, K is equal to 8 rho dAB by rho L into ln 1 plus By. Now, from these expressions we find out a relations which we normally call this as a d square law. So, d square t, that means square of the droplet diameter at time t is equal to its initial diameter square minus k times t. So, with lapse of time the diameter shrinks. So, basically if you look at this particular figure, we can plot the d square versus time curve, and eventually it is, this equation says it is a straight line with a negative slope, that means size of the droplet decreases with time, and what particular time Td, this at Td diameter goes to 0, that time we call this as a droplet lifetime. Another point I need to emphasize is that in the combustion terminology, we use the parameter as square of droplet diameter, which is more familiar rather than the droplet diameter. D square law says that it is a square of the droplet diameter, which is a more appropriate term in combustion terminology. Then moving further, it says that we define this droplet lifetime. We say that time taken by the droplet of a given initial size to evaporate completely is known as the droplet lifetime, and the d square varies linearly with time with a slope of minus k, and k stands for the evaporation constant. Then moving further, so we now need to look into this droplet evaporation with respect to heat transfer point of view. So if you look at this particular figure, what it says is that same droplet, it is in the conditions when it is being injected, it is in the engine cylinder, it has certain temperatures, and that temperature is T infinity, and here we call this as a far field temperatures. So the droplet is seeing and ambient conditions where the temperature is T infinity, whereas the droplet surface temperature is Ts, and typically this Ts happens to be T boiling point, which means that droplet is about to evaporate. So at that point of time when the surface temperature is close to its boiling point, it is about to evaporate. So if you look at the conditions which is at the droplet surface Rs, and here we have ambient conditions. So temperature is T infinity. So the droplet temperature keeps on increasing. How long it will go? So initially to start this temperature, it is at its boiling point, and finally when it goes, it can go up to maximum free stream temperatures T infinity. So this is the temperature distribution curve, how it should look like. So physically what happens is that heat from the ambient environment and supplies energy to the liquid fuel. So this energy allows the fuel vapor to diffuse from the droplet surface to the ambient gas, which means the mass loss. So when this droplet evaporates, there is a mass loss. This mass loss causes the droplet radius to shrink with time until the droplet is completely evaporated. So let us see how this particular concept we are going to model. So there in the previous study, it was the concentration difference in terms of mass fractions. Here it is the difference due to the temperatures. So similar philosophy we are going to allow. So first thing, we need to determine the mass flow rate of the droplet of the fuel vapor. Second thing, we must calculate the how the droplet trace varies with time, and finally we are going to calculate the droplet lifetime. But here the concept is eventually it is between the balancing the heat transfer equations. In similar philosophy, the following assumptions were considered. The droplet evaporates in a quiescent and infinite medium. The evaporation process is quasi-steady, which means the process can be described as the steady state at any time instant. The fuel is considered as a single component liquid with zero solubility for gases. The droplet temperature is uniform and it is assumed at the boiling point of the fuel. And here also there is a parameter called as Lewis number, which is defined as the ratio of thermal diffusivity to the diffusion coefficients. So there is no mass transfer with it, but both the ratio is unity. Ratio unity means Lewis number is unity means both have same effect. The thermophysical properties such as thermal conductivity, density, specific heats for the droplet are treated as constants, although they vary with respect to surroundings, but our assumption talks about the constant property situations to allow for closed form solutions. Now when you do this, we need to recall about governing equations, and they are gas phase mass conservations, gas phase energy equations, droplet gas phase interface energy balance, and droplet liquid mass conservation equations. I am not deriving it, it is available in the books, but what I am trying to say is that how the energy balance takes place at the droplet surface and in the gas phase. So, what we look at in the gas phase. So, in the gas phase means already the droplet has vaporized. So, prior to that on the droplet surface there is a heat or enthalpy which is the mass flow rate into H liquid, means enthalpy at the liquid state, and that goes to the vapor. So, it is a latent heat. So, that goes, and that things at the same time along this droplet surface there is a Q conduction that happens. So, that means this energy is going to balance with this Q conductions that comes from for this spherical bubble. And again in the gas phase we are looking at the certain layers at different R. So, one is R, other is R plus dr. So, there the difference between these two radius is delta R. So, along this delta R we can find out the energy balance for this delta R locations. Now, when you do this we can write this energy conservation equations, and the boundary conditions what we look at already have mentioned. At R is equal to infinity the temperature is far streams T infinity. When at R is equal to Rs, at the surface, we say that it is at the boiling temperatures. So, ultimately in the end what we are going to recall is that evaporation rate we need to find out, and if you look at this expression closely, this resembles similar to that of heat transfer analysis study, but only difference that we have here, the parameters involving thermophysical properties such as thermal conductivity in the gas phase, specific heat of the gas phase. Of course, radius of the droplet is already was there in the previous expressions. What other difference that we have is the transfer number, but here the transfer number BQ is defined with respect to heat transfer. So, BQ is nothing but Cpg times T infinity minus T boil by HFG. So, this transfer number is defined with respect to this. So, in other words what we say, we are able to express evaporation rate as a function of transfer number. Now, when you do this, then we are now able to frame how a certain initial size of droplet shrinks to 0 diameter or when it completely evaporates. So, based on this we are now able to find the droplet lifetime Td, and by which the initial size of the droplet d0, its size drops after certain time with a negative slope minus k, and this negative slope is a function of the thermophysical properties and the transfer number, and this k here we call this as evaporation constant based on the heat transfer, and BQ is the dimensionless transfer number based on heat transfer. So, based on this we are now in a position to express the evaporation constant KQ and the transfer number BQ. From this we can recall the mass balance expressions. In a transient study we say that rate at which mass of the droplet decreases is equal to the rate at which the fuel is vaporized. So, talking into these things, so we can start with dmd by dt is minus m dot. For putting its geometrical parameters and putting these expressions for the m dot, we can arrive at the d square law, which says d square t is equal to d0 square minus kqt, and this is also a linear relations. So, having said the droplet evaporation by mass transfer and heat transfer, we are now in a position that we can think of that situations where the droplet has already evaporated and flame has been generated. When the flame has been generated, so droplet is within the flame. So, in a situation that within certain flame range there may be multiple number of such droplets possible, and in this case the both temperature as well as concentrations become significant parameters. So, we are now going to study the combined effect of temperatures and concentrations with respect to droplet evaporations, and subsequently we are going to calculate the droplet lifetime. So, the extension of mass and heat transfer of droplet evaporation leads to the subsequent development that includes a spherically symmetric diffusion flame that surrounds a droplet. Now, in this case, the uniform temperature which we assume to be at boiling temperature is now relaxed. That means analysis becomes more complicated. But however, there are certain assumptions that has to be considered to frame these governing equations and finding its solutions. The burning assumptions are as follows. The burning droplet is surrounded by a spherical symmetric flame and it exists in a quiescent infinite medium, and there is no interactions with any other droplets, so that convection effects can be ignored. The droplet burning process is treated as a quasi-steady. The fuel is a single component liquid with zero solubility for gases. The phase equilibrium prevails, that means there is a phase equilibrium at the liquid vapor interface. Pressure is uniform and constant. Radiation heat transfer is negligible. Then the gas phase consists of three species: fuel vapor, oxidizer and combustion products, and it is divided into two zones. One is inner zone between the droplet surface and the flame containing the fuel, that fuel containing only fuel vapor and products. Outer zone contains the oxidizer and the products, and the binary diffusion prevails in each regions. Now, when you deal with reactions, the fuel and oxidizer react in a stoichiometric proportion at the flame. The chemical kinetics is very fast, so that the flame can be treated as a very thin regions or very infinitesimally small sheet. The thermophysical properties such as gas phase thermal conductivity, specific heat, product density and mass diffusivity are constants. The liquid fuel droplet is only in condensed phase without any soot and water. The Lewis number is taken as unity. So, these are the assumptions that we have for the droplet burning, and I need to emphasize more on this particular diagrams to emphasize what is this inner region and what is this outer regions. First, to recall that this is your the droplet, spherical droplets that varies with size changes with time. At one particular point, this droplet has certain surface, and from this viewpoint we can say that somewhere we can define a flame which has certain radius RF. So, we say it is a flame which has certain radius RF, and within this there are two zones, one is inner, other is outer, and this inner range stands from RS less than equal to R less than equal to RF, and within this inner range we can define the surface temperature at this droplet surface as Ts, and at the flame it is temperature as Tf. This is the first thing. And when you go to the outer regions, that means when Tr is equal to Rf is equal to Tf, this is the first boundary conditions, and when R goes to infinity, so we say it is a T infinity. So, this is the T infinity, and so this is what we call as outer regions. Now, if you look at the temperatures things, so this is where we have liquid surface interface at radius Rs, and this is where we see this the flame sheet at radius Rf, and within these inner regions we can see that obviously there will be an increase in the temperatures. How long it can increase? It can go up to the flame temperature Tf, and typically one way to assume that maximum flame temperature could be TAF. So, somewhere in this domain we can drop another fixed line, which is we can call this as T adiabatic. So, adiabatic flame temperature may be above this line, which is a fixed line, but after this flame sheet this temperature again falls down. So, this is how the temperature curve, and irrespective whether we have fuel, oxidizer or lean, rich. So, this is the temperature distribution. Now, when you look at the effect with respect to concentrations, we see that in the vertical line, if you talk about mass fractions and mass 1 at Rs, it is at this particular surface there is no product formed, but the fuel has highest mass fractions on the surface, but 0 or close to 0 products at the Rs locations. So, with time or with increase in the radius, what happens, the fuel mass fraction drops. How long it drops? It will goes to 0 at the flame radius, and the same flame radius your product concentration goes up, shoots up, and it goes to close to 1. Then beyond that happens in the regions. In the outer regions, if you look at the product value, that drops down, and whereas on the flame sheet this again we have this concentrations, this fuel concentration goes up. So, this is what we call as a droplet burning model, and in this case one important segment or point to be noted is the Lewis number, which gives the combined effect of mass diffusivity and thermal diffusivity. So, that is the ratio of that means alpha by D, and this alpha, that is thermal diffusivity, is rho Cp by K. Okay. So, based on this I think I have explained this. Then we are now moving on to the another aspect, what happens at the liquid surface or gas interface. So, this is the interface location. So, interface location means this is a liquid and this is the gas phase, and at interface liquid region we define the partial pressure of the fuel vapor in an exponential manner. So, partial pressure of fuel vapor is A times exponential of B by Ts. Ts is nothing but the surface temperature of the droplet, and typically one simplest way to use the value of use the boiling point. And then at these things we can recall our earlier equations, Clausius-Clapeyron equations for a two-phase system. So, this we derived when we are discussing about the thermodynamic property relations for a two-phase situations, and you can see its utility at these locations where we are seeing liquid and gas phase, and we are looking some kind of relations which can fit to solve this fundamental concept of droplet burning. So, here we need to recall this Clausius-Clapeyron equations, and by considering this it is possible to find the fuel mass fractions, it is possible to find the A and B. So, all these things that has to be taken into account while solving this droplet burning equations. So, ultimately by considering all these aspects we need to study the two things. First thing, we need to determine the similar way which we call as droplet burning rate for a given droplet size and the conditions which is far from the droplets. So, we also need to calculate the lifetime for the droplet. So, for that droplet lifetimes needs to be calculated, D square law has to be found out. So, this is the very basic concept that we need to do. Now, to get all these things through this process, what we also have to find out is the expressions for describing temperature and species profile along with the relationship with the flame radius, flame temperatures, droplet surface temperature and fuel mass fractions. So, this quantity needs to be found out first to arrive at the D square law and other subsequent analysis with respect to droplet size and the droplet lifetime. So, basically there are 5 equations that needs to be invoked. One is energy balance at the droplet surface, energy balance at the flame sheet, oxidizer distribution at the outer regions, fuel vapor distribution at the inner regions, phase equilibrium at the liquid phase vapor interface. That we did it, that in the last slide we talk about recalling Clausius-Clapeyron equations. So, this particular picture shows the surface energy balance at the flame sheet at the liquid vapor interface. This particular expression shows the mass flow relationship at the flame sheet. So, basically along this flame sheet there are two parameters, which is m dot into Hf, and that is for the fuel. The other side is you have oxidizer and we have products. And at the interface of liquid and vapor there is a balance of heat, that means a specific enthalpy in the liquid state and specific enthalpy at the vapor state. There are a difference, and in between the difference in both the thing is nothing but your latent heat. So, by considering this, we are now framing the following relations. First one is fuel droplet mass burning rate. So, this is again with respect to thermophysical parameter Kg, Cpg, and one more number we recall BOQ, and this is nothing but your transfer number for droplet burning. And if you see these expressions, this expression is different than that of other two situations like mass transfer and heat transfer, because this analysis was done with respect to flame as well as the droplet simultaneously. So, it involves the specific enthalpy of combustions, then stoichiometric air fuel ratio, and this specific heat in the gas phase and enthalpy difference between liquid and gas phase, far field temperature and TS. TS stands for surface temperature, and far field temperature can be up to the T infinity. We can have two approximations. One is this T infinity can be at flame temperature, or T infinity can be at adiabatic flame temperatures. So, with this one can see that what is the role of this droplet burning, and accordingly this has a net effect in calculating the droplet lifetime. Then we can find out the fuel mass fraction of the droplet, droplet surface temperatures, then flame temperatures, flame radius. All these numbers can be calculated by knowing these thermophysical properties, and of course we also require to know the molecular weight of fuel, products, and partial pressures, total pressures, fuel mass fractions, and so on. So, this will give you the value of all these numbers. Now, after knowing all these things, we will be now able to find parameters, and here the parameter we call this as a droplet burning rate constant. This number is similar to the droplet burning rate constant, which is similar to the previous value of K, and here what is the difference that changes is nothing but your transfer number expression, that is a different number, and this transfer number is, we have to get it with the combined effect of flame as well as the droplet. So, based on this rate constant we can be able to frame the d square law, and this with this d square law we can find out the droplet lifetime, d square by k. So, we can find out the droplet lifetime. So, this is all about the droplet burning, which talks about the combined role of heat and mass transfer during the burning of the droplet. So, this concludes the lecture part for this module, and of course towards the end we are now going to discuss one simple numerical problems based on the understanding of droplet burning, mainly droplet burning. So, we are going to consider the combustion of n-heptane droplet. So, the word n-heptane normally we use in the diesel engine combustions. While calculating the certain number, n-heptane takes a very crucial role. That means it is the ideal fluid for diesel engines. So, we are looking at the droplet of n-heptane fuel, and its initial size is supposed to be 100 micrometer. We need to find out the mass burning rate, flame temperature, ratio of flame radius to droplet radius, at atmospheric conditions. Assume quiescent surroundings and the droplet is at boiling point. For the solutions, please refer the expressions for droplet burning. So, you have to recall the expressions for the droplet burning. Apart from this, we also need to find the data. That data refers for a fuel which is N-heptane. So, N-heptane fuel has a molecular formula C7H16 and it has molecular weight 100. So, of course, molecular weight for air is 29. Then other parameters we are looking at the quiescent surroundings. Surroundings in this case we say it is T infinity as 300 Kelvin. Surface temperature of the droplet is nothing but boiling point temperature, and for this fuel, that is N-heptane, this number is 371 Kelvin. We also require CP for gas phase, which is 4.22 kilojoule per kg Kelvin, that is for N-heptane. Then delta Hc, that is enthalpy of combustions, is 44926 kilojoule per kg. Other parameter we require thermal conductivity kg 0.0926 watt per meter Kelvin, and diameter is, or initial diameter is D0 is 100 micron. So, RS surface is 50 micron. Then what we do not know is nu, which is stoichiometric air fuel ratio. To do that, we have to recall this fundamental combustion equation Cx Hy for a combustion of a hydrocarbon fuel, A times O2 plus 3.76 N2. This gives rise to X CO2 plus Y by 2 H2O plus 3.76 A times N2, and nu, that is air fuel ratio, is 4.76 A molecular weight of air by molecular weight of fuel. Now, here what is A? A is equal to X plus Y by 4, and in our case X is 7, Y is 16, so A becomes 11. So, when I have this, then first thing we can calculate nu. Nu is 4.76 into 11 into 29 by 100. That expression is 15.2. So, we have all the parameters. So, we have to recall our expressions. So, first parameter we calculate m dot f, and m dot f is nothing but mass burning rate. That expression is 4 pi kg into Rs divided by Cpg ln into 1 plus BOQ, and where BOQ is delta H by nu plus Cpg into T infinity minus Ts divided by QIL plus HFG. For the time being, let us take this number as 0 because at the interface both the heat balance. So, this number is 0. So, by putting this we can find out this BOQ as 8.5 and m dot f becomes 3.1 into 10 to the power minus 8 kg per second. So, mass burning rate is or droplet evaporation rate is 3.1 into 10 to the power minus 8 kg per second. Second part is flame rate temperatures TF, that is QIL plus HFG divided by CPG into 1 plus nu BOQ minus 1 plus TS. Now, all the numbers is known from the data. So, flame temperature is 962 kelvins. So, all these numbers can be put in this expression and flame temperature can be found out 962 Kelvin. Third parameter is radius RF is equal to RS times ln 1 plus BOQ divided by ln 1 plus nu divided by nu. So, this will implies RF by RS, which is non-ratio of flame radius to droplet radius. That number is 35. So, we can say droplet radius is 35 times smaller than the flame radius. Now, second part of this problem, we need to find out the lifetime of the droplet and how does it compare with pure vaporization with far field temperature of this. So, basically we are going to compare burning versus pure vaporization. So, in this case the difference will be the transfer number. So, we need to find out the transfer number for burning, which is BOQ, and for pure vaporization this transfer number is BQ. So, with that difference we need to compare. Second thing, two far field temperatures, that is I was mentioning, one is 1927 degree centigrade, this is close to 2200 Kelvin. So, this is typically we are calling this as a adiabatic flame temperature for hydrocarbon fuel. Other is 689 degree centigrades. 689 degree centigrades, which refers to flame temperature in our previous question 1. So, this is flame temperature. So, if this is the situations, we are going to find what is the lifetime for this droplet. So, the problem is very simple. So, we can first find out for the first case, when you say to do this, we need to find out rate constant for the droplet burning, which is 8, expression is 8 kg rho L into CPG ln 1 plus BOQ. So, all these numbers we have previously found out. So, we have BOQ is 8.5, kg is 0.0926, thermal conductivity watt per meter Kelvin, CPG 4.22 kilojoule per kg Kelvin, liquid rho L for you will be 684 kg per meter cube, that is density in the liquid phase for the fuel, and in this case it is N-heptane, and initial diameter D0 is 100 micron. So, putting this number we can find K or rate constant as 5.8 into 10 to the power minus 7 meter square per second. Then subsequently we will find out droplet lifetime. Td will be d0 square by k, and this number is 0.018 second. First thing. Second part, pure vaporization. This is the part we say burning. When we say pure vaporization, so BQ instead of BOQ, we will be using the expression BQ, that is CPG T infinity minus T boiling divided by HFG. Now T infinity can have two numbers, one is 2200 Kelvin, other could be 962 Kelvin, 689 degree centigrade, and this is nothing but your flame temperatures as derived in the question number 1. So putting this, we can have, if you say T infinity is equal to 2200 Kelvin, we will have BQ as 24.42, boiling point is 371 Kelvin. Okay, we have BQ, and this will give you K, rate constant will be 8.3 into 10 to the power minus 7 meter squares per second, and putting this K, we get Td is equal to d0 square by k, and that number is 0.012 seconds. So you can see that in this case, when you do call about the pure vaporization, we expect droplet lifetime is 0.012 seconds, and which is not a, for which we can say there is a large difference. So the idea of talking about T infinity as 2200 Kelvin is not a realistic, rather we should see this T infinity close to the flame temperatures. So instead of that, this particular things, if you say T infinity is close to Tf and goes to Tf, and that is 962 Kelvin, so we can find BQ as 8.6, K would be 5 into 10 to the power minus 7 meter square per second, and Td will be 0.020 seconds. So you can say that when our ambient condition is approximated at the flame temperatures, the pure burning model and pure vaporizations model, they give a close resemblance, close matching. So this gives the fact that pure vaporization model with very good approximations can also lead to the concept of droplet burning. So this is all about this lecture for today. Thank you for your attention. Once again, thank you. So let us close this session.